I'm constantly seeking for improvement in chemistry, okay? You can always improve. You can always learn nomenclature better. You can always do reactions better. You can always do canceling units better in stoichiometry, whatever it is, okay? And some of us are fantastic at this right now, like unbelievably fantastic. Some of us need a lot more practice. So I can't let one person be rewarded and not the other. So what I need to do is we need to continually work on stoichiometry, because you're going to see today that stoichiometry comes back in with gas laws, because we're going to start putting gas laws in chemical reactions, right? Reactions that make gases. It kind of has a natural progression from gases to reactions with gases to stoichiometry. So if you are still struggling with stoichiometry, you need to improve. You can come to tutoring and improve. You can do this by yourself, but I need to have some incentive. Your incentive is, if you've not seen this on my website already, under tonight's homework, here it is, okay? I'm rewarding you for continually improving. The two options are you can get up to 14 points, because you can do 10 reactions for 0.7 points each, and or 10 stoichiometry problems for 0.7 points each. Basically, you need to continue working on stoichiometry nomenclature. Heck, I'm going to even have a pop quiz, nomenclature quiz one day. It should be an easy 100 for most of us. Some of us who still don't know how to crisscross, we need to work on that. So you must, for the first option, you must write out a chemical reaction, aka methane combust. Okay, write it out, and so when methane combusts, it makes water and carbon dioxide. So I'm writing it in word form first, and then I'm writing the BCE for it. That's an easy point stack, okay? But if you do all 10, do a combination of synthesis, decomp, single, double, and combustion. If you do all the stoichiometry problems, please mix it up as well. But the stoichiometry problems are basically you writing out a stoichiometry problem like you had on your problem set 12, like 10 grams of hydrogen reacts with 10 grams of oxygen, how much water can be produced? Okay, simple question, but show the solution for it as well. So you can get up to 0.7 points back for each of these. This is a sum of 7 points here, 7 points here, so 14 points total. You cannot, if you did not already exceed 100, you can only get up to 100. So if you got a 97, do a couple of these, get yourself up to 100. If you already exceeded 100, stop listening to me now. Okay, thank you. If you are sitting at a 50, please get this done. This is due Monday, okay? Because we need to practice our stoichiometry, because you have a test on gas laws on Friday, which includes a little reaction stoichiometry. We're like over halfway done with gases. Okay, gases are really short and really easy. So if you would like to start doing this now because you're done looking at your quest, do so while I finish checking the rest of your homework, okay? Otherwise, start on problem set 14. Give me a second so I can finish checking. I got a couple things on our to-do list for today. Okay. Ready? Set. Shh. So I'm bouncing around a bit. I want free time at the end of class so you guys can ask me questions on the 1 through 16 homework. So those of you who have not checked yet, keep it on your desk because I'm going to be rotating to you, okay? So first thing I want to do is review our gas laws. We should know. What's Boyle's law? Gage, what's Boyle's law? Boyle's law. Benny. Yes, P1 equals P2 V2. It's just you got to know the person's name with the law, okay? Straw, what's Charles's law? Charles. Yeah. Right, so that's the one that's over top of each other. Boyle's law is the only one that's side by side. Avogadro's law, Shannon.
It's N1 over P1 equals N2.
Good. Gay-Lussac's, Keith. Look at your stuff. Okay, so all those variables you're stating, those are the ones that are changing throughout the experiment, but the other variables you're not saying are what? So like for P1 equals P1, B1 equals P2, B2, what's not changing? Temperature and moles of gas, right? So in a problem like you saw on I think number 12 and another one, sometimes miscellaneous information is given to you in the problem, like they'll give you one volume but they won't give you the other. So that actually is saying to you, this volume is constant. It's just an extra piece of information. So scratch it out if you feel like it's a distractor, and then go along with your normal gas laws. Okay, so we'll keep practicing this. You'll see a lot of this on your problem set 14. It'll get you really well prepared for your test. I have problem set 13 key up here, and I'll go over it at the end of class if we have time. So let's go into theories. And then at the end of class, we'll have some time to go over your 1 through 16. Okay? So theory. So we're going to do notes first, practice, keep your concepts of your 1 through 16 out, because I'd like to finish checking those. Keep your test out so you can have that for yourself. I'm back in like 2 days maybe. All right, so laws versus theories. Give me an example of a law, Gianna. An example of a law. Huh? Okay, law of conservation. That's what she's sticking with the chemistry. I was thinking like law of gravity, Newton's law, and stuff like that. Stuff falls. There's gravity for you. Did I explain anything? No. Okay, law of conservation, mass. Stuff is conserved. Mass cannot be created or destroyed. Did I explain anything there? I know you're not that smooth. Okay, so laws are very simple and they're quick and to the point, right? What's different between laws and theories then? Yeah. Okay, so they're very long-winded, very explanation-based. They have a lot of data to support them. And we use theories to actually make our lives easier, okay? So Vesper was one of our theories we went over already. What was Vesper? Valence. Shell, electron, pair, repulsion theory. Okay, Vesper, valence shell, electron pair, repulsion theory. Basically, we're like, hey, on the central atom, there's some electrons, and those electrons push other electrons, and they make a shape. Tetrahedral, bent, trigonal planar, trigonal pyramidal, stuff like that. Okay, very long-winded, but it's actually that's not always all the way true. But we stick with it because it makes our lives easier. And that's why we have the little chart in the back of our electronegativity chart. We're like, oh, 2 lone pairs, 2 ligands, bent. It's like a quick, easy rule to go with, right? So, for theories in chemistry, we also deal a lot with models. Models that help us to describe how matter reacts and how matter acts. And it's just basically an explanation to that everybody can halfway agree on. Now, it's not, you're right, it's not all the way proven, but it's our best explanation that we got. But sometimes theories kind of take everything as a whole, and they're like, oh, everything follows the rule, this theory, the kinetic molecular theory. Everything follows the Vesper theory. Everything follows this. That's lumping everything together. So sometimes theories are kind of lies that make us feel good about ourselves. Okay, we can deal with that. So we're going to talk about how the kinetic molecular theory describes ideal gases. What are these two important words? What do they mean? What does kinetic mean? Motion. We're talking about things moving, right? So we're talking about things being in motion, and molecular refers to molecules, right? Like gases, for example. Okay, don't forget molecules are nonmetals, or just simply like diatomic nonmetals. Okay, so we're talking about how these things are related to gas and how moving relates to this particular theory. Ideal, though, this is a new word, ideal. Who thinks they're my ideal student? So many confident people, so many confident. If I can mesh a couple of you, just a couple of you, I can do that. Okay, now here's your turn. Close your eyes and imagine that ideal guy or that ideal girl. You see them? They're perfect in all ways. They make you dinner, they take you out at night, they pay for your movie, they help you when you need it, they make you coffee in the morning, what else? What else?
Buy you flowers.
Buy you flowers, what else?
I love it when girls buy new flowers.
They let you wear their t-shirts.
Let you wear their t-shirts,
Yeah.
oh yeah. Super ideal. Yeah, so like the perfect guy or girl, they're
Big
out there, right?
biceps. Abs.
Abs, six-pack, I can do that. Okay? So, basically, you're telling me, is this ideal person out there? Is this ideal person out there? Have you ever met them? No? Look, I'll be honest. I'll be honest. Even my husband doesn't make the coffee right all the time. But he makes me coffee every morning. I can't complain. But today's coffee is a little weak. But I'm not going to tell him that because I want him to make me coffee. Okay? Like I have to get into that, right? But I'm not going to constructive feedback, right? So he's super, super, super close to ideal. But you know, there's still those little things, minor fixes you can make, right? So what we're talking about is ideal gases. So do you think ideal gases truly exist in nature? No. But hey, we can assume they exist, because if we assume they exist, we can assume this kinetic molecular theory is correct, and that means we can assume really simple math. Because if you assume that all gases are real gases, then we got math on math on. Guess what? Yes.
My mom's in the hospital. So can I go home? She's a nurse.
I was feeling kind of bad for a second. Okay, anyway, let's get this done. Stay on track with me. Okay, so we assume information about ideal gases because we get to use something called the ideal gas law. If we assume things are all real gases, our math becomes a little bit more tricky. So we do a lot of assumptions. We lie to ourselves essentially to make our lives easier. Are you okay with lying to yourself just a little bit? Yeah? Like, you gotta be okay with it, because I'm okay with it as well. Okay? So, we assume that that all gases have essentially no volume. Basically what we're saying is that they're so tiny, they essentially take up no volume of their vessel in which they are sitting in. So if we have a 5-liter vessel, or, you know, it's called a vessel, just like a reaction chamber, then they have the full 5 liters to go play in, okay? But truly, real gases, guess what? They do have volume, okay? So, of the 5-liter vessel, you know, there might be 5 liters that they can go play in, but they take up a small portion of that volume. They might take up 0.05, so they don't have the full 5 liters to play in. They have 4.95 liters that they essentially, that's open space. Okay, so basically they're taking up space, so they don't have that space to move about in. If we assume that they have no volume, we assume that they have a full 5 liters to react in. And that does make a difference in some of our reactions. Okay, ideal gases, we assume that they're in constant random motion. Okay, we assume they're in constant random motion under this kinetic molecular theory. So tell me about real gases then, for real. Here, I'll give you a hint. Constant random motion means that they don't interact. They don't collide, they don't do anything. They don't collide very often. They do collide. They don't interact. So INTXs interact for me, okay? So what do you think real gases do? They do interact, right? They do interact. Now, interactions, what were those interactions between molecules we talked about? What are they called? Interactions between molecules. Intermolecular forces. So, if I'm a polar water molecule, and I'm zooming by, randomly, constantly moving around, and I see another polar molecule, what are we going to do? We're going to be friends, and we're going to interact via hydrogen bonding or dipole-dipole, right? Let's see a nonpolar molecule. Repel, right? So we're not going to interact. So we have some problems here, because if they start to interact, they're no longer in random motion. So IMFs come into play in real gases. We assume they don't in ideal gases. Our next assumption for the ideal, or the kinetic molecular theory, is that particles have elastic collisions. Elastic collision. That basically means particle 1 and particle 2 hit each other, bounce back with the same exact velocity. So no energy was lost in that collision. Elastic, like a rubber band. It goes 100% back to what it was before the collision. So particle 1 is flying this way, particle 2 is flying, they hit in the middle, and we assume no energy is lost, 100% efficient. So what do you think really happens? Okay, so there's a transfer of energy, or energy is lost, right? So it might be like two particles coming together, this one's moving fast, this one's moving slow, it hits it and moves it, but then they both move slower. So if they both move slower than they are intended to, then the kinetic energy has been lost. So collisions result in kinetic energy lost. And I'm going to put in parentheses friction, because a lot of times it is due to friction between the molecules in which they lose some of their energy. Yeah. Question? Oh. Never mind. Okay, we have two more here. So this one is a proportion, so it's a description. Kinetic energy is directly proportional. You know the fish sign? Fish means proportional. If you didn't, you do now. Okay. Kinetic energy is proportional to temperature in Kelvin. Remember we talked about the soup last week and blowing away the kinetic energy of the molecules with the highest kinetic energy. What did it do to our soup? Less warm. So it pulled down the temperature, the average temperature. Good. So kinetic energy is proportional to Kelvin. This is actually true 100% of the time. True always, because that's true for ideal and real gases. Or assumed la la land real ideal for real world, real gases. This is like the super longest slide here, okay? Last postulate, or the last assumption we make from the kinetic molecular theory is, we assume, this one is related back to that other one, the second one we talked about, we assume they do not attract or repel each other. So we assume there are no IMFs at work. But really, for real, guys, we know IMFs are at work. We know they are present. And that actually causes problems, because how does pressure occur? Like, what's the definition of pressure? We talked about this last week. With the container wall, right? So if we're both two gas molecules, right? We're colliding with the container wall, we're being against all head, right? But then what if we're both polar molecules may touch each other and we stay? What's going to happen to the number of collisions with the container wall? It's going to decrease by half, because no longer are we two separate entities, we're one entity. So it actually causes a difference in our pressure, which is problematic. So that's why we do this assumption. We lie to ourselves a little bit, because if we have to account for differences in pressure, and differences in volume, and differences in IMFs, we got a big, huge math problem on our hand, and we got to kind of keep it simple for us here. Okay, can I go forward? We do a little bit picky, yeah. We talk about the non-ideal gas law and the ideal gas law. But we don't do a whole lot of calculations. That's more of a college thing, like second year college level. Okay, so this is a graph that is supposed to show you that you can change conditions and you can force things to act ideally or force them to act real. Real gases, they do interact, they do have volume, they do all these other things, right? So I'm going to show you with your box of air. You got it today? You didn't forget it, right? You got it? Box of air. Okay. Hopefully you didn't forget it. Make up one. Okay, your box of air. I want you to create a high pressure situation here. Okay, so now the gas molecules, they're squished together, right? So what do you think they're going to do with each other? They're going to collide more. They're going to go, hey girl, let's hang out. They're going to interact, right? So now you're forcing them to act real because you're forcing them together in intermolecular forces. Okay, so now open your box back up, normal pressure situations. Now, pretend you're a gas molecule. You're zooming around like crazy, running around, right? Now the temperature drops. What's happening? Okay, you're slowing down, so then what happens? What are you able to do? You're able to stop and say, hey, how are you doing? And interact with another gas molecule. If you're flying by another gas molecule because your kinetic energy is so high, there ain't no way you're going to interact. You're just zooming past each other. If you slow down, you can stop, and then you guys can hang out, ask how your weekend was, and stuff like that, right? So, real gases are going to be, gases are going to act more real under these two conditions. High pressure because they're smushed together, low temperature because they're slowly moving past one another. That's when they act real. And another way to say that is they deviate from ideal behavior. That's another way to say they deviate from ideal behaviors. They're doing all the opposite things that an ideal gas would do. And this graph is showing you that because this is the ideal line right here. If anything was ideal, it would stay really close to this green line I've just drawn here. But this pressure increases this way to the right on the graph. So what is it showing you at a high pressure for all these gases? What's happened as we've increased in pressure? They're not as close to the line, so they're deviating from ideal gas behavior. They're more real gas-like than ideal gas-like. Okay, so that's all we have to talk about for ideal gases. Now we can do calculations. Basically, the kinetic molecular theory supports our thoughts on how do gases normally act under ideal conditions, and we can calculate with it. Oh, I forgot to show you this too. Oh, darn it. Okay, so I'll show you more about the KMT. These are just basically characteristics of gases. Did you know gases have low density? Yeah, okay, a lot of these are common sense, okay? Low density. They float. Good thing, because my mouth's up here and I need oxygen up here, not down on my feet. Okay? We also know, you know what you've been doing with your gas? What are you doing it? What are you doing with it? You're compressing it, and then you can also let it expand. Okay, so these are two more characteristics about gases. Basically, there's space between, there's nothing between molecules, so there's like a molecule here, here, and here, so there's area in which you can squish them together or let them expand back out. So those are two common sense ones. I also think this one's common sense. What is the definition of diffusion from biology?
That's great.
But moving it from what to what?
I love it.
High to low concentration, right? So particles, so if I brought in a box of Krispy Kreme donuts for you guys that like you so much. I don't run the 12 though, so only my ideal students. So if I brought these in, who would be it's really concentrated right in the box. Who would be the first people to smell it? These couple people. And then it would matriculate here, 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 and here, and eventually back to that corner of the smeller, right? So what am I telling you that the gas molecules are doing? They're diffusing from the high concentrated donut box to the low concentration noses on that side of the room, right? Now, these molecules, they're really, really light. They're really low mass, low weight. This is the important part that you've not written down yet. This is a non-common sense one, but after I tell you it will be common sense. Ready? Okay, so I'm going to scooch down here to look at this formula. This is kind of like a physics/chemistry formula. Anybody in physics or world in physics, you'll see this again. Any gas molecule, the velocity of it will vary based on its mass. So this is the formula you need to understand and know. Mass is what M stands for. V is velocity, kind of like speed. That's what that V stands for. So it's 1/2 mv squared. Who's ever seen this formula before? A couple of us, okay. So think of, let's see here, my brother was a wide receiver. He was a little skinny dude. He'd run out there, jet out there, get the ball, touchdown, right? Superstar. But one time, let's see here, got to the goal line, and this guy like side tackled him and he hit his arm down, and his bone came out the bottom of his arm. He's like that, maybe more. I don't know. He basically couldn't play again for like the next season. But anyway, what I'm telling you is that he was moving fast, right? So basically his mass was low, so his velocity could be high because he had less mass to carry around. The hiker, the center hiker, he was probably not going to go down the field and go catch the football from a long Hail Mary pass, right? Probably not. Because usually they put more massive people in that position, so because their velocity is fairly low. Okay, so I like saying it as a sports example. But you should know, big things move slow, small things move fast. Does that make sense? Now it is common sense, so you should know this. The last definition you had on reading guide 14 was effusion. And here's an example of effusion. What am I showing you? What did I do to the poor balloon? I put a hole in the balloon, and the hole in the balloon allowed for the gas molecules to escape. So, what molecules do you think will escape fastest? Helium or carbon dioxide? Helium, because it's lightweight, right? Carbon dioxide will stay in the balloon because it travels at a slower rate. So we're going to talk about effusion a lot more tomorrow and Wednesday, but it's basically that whole equation here, but based on molar mass, adding it up. Okay. You guys are sleepy on me today. Write down this information about the ideal gas law, and then we'll do a practice problem, and then I'll give you guys a break. I gotta finish taking homework. You're good. Okay, this unit right here, I'll expand this a little bit, or bring this up. This is ATM per liter over mole K. Okay, so the ideal gas law is based on the kinetic molecular theory assumptions we were talking about, so we can only use this law when we assume all those assumptions. So that's why you gotta lie to yourself a little bit, because we get to use this law if that's the case, right? So PV equals nRT is the formula. P, V, N, and T are going to be given to you in the problem. All but one of them will usually, because we're going to be solving for one of the others. R, I will always write down for you. You will eventually accidentally memorize it because you're going to use it a lot in your problem sets. But R is this big, huge constant, 0.0821 atmosphere per liters per mole K. Okay, 0.0821 goes on the numerator. Atmosphere liters per mole K is in the denominator. Mole K is in the denominator. So we can use this when we assume behavior ideal gases. Now this one is special. So on problem set on the questions 1 through 16, I could give you pressure in any pressure, right? As long as they're in the same pressure units, you were fine to use them, right? What did you have to do with liters? I mean, with the volume, did it matter? Milliliters, liters? Not really. Temperature? Convert to Kelvin, always. 100% of the time you had to convert to Kelvin. But with the ideal gas law, you don't get to pick your units. The units are given to you. They are given to you in the gas law constant. So your units must match that, or you're not going to have the correct answer. You're not going to cancel out. So pressure must be in what unit? Atmospheres. Volume must be in what unit? Liters, amount, moles, and temperature, Kelvin. Okay, so let's do an example practice problem with this. So the units of the R value is the universal gas law constant, guide you to what the other ones must be, and so you can cancel them out. Okay, I think pull out your 1 through 16, because on the next ones are the ideal gas laws. Yeah, we're going to do number 17 and 18 and 19. 17, 18, 19. So work with me through those so you have something to look back on. (17, 18, 19). I'll give you a stretch break after that. Some of you guys are sleepy on a Monday morning here. You gotta have somebody make you coffee in the morning. But just don't complain this week. Oh, sorry. Okay, so 17 has a lot of information in the first part of the problem, okay? So I'm going to show you how I want you to set it up. That way you'll never get it wrong, okay? So it's just me trying to protect you from your own self. 17, I'm going to stop and ask you to tell me what to write, okay? A student collects 425 milliliters is what variable? Volume, okay. Student collects 425 milliliters of oxygen gas. I'm just going to put O2 over here just for kicks and giggles, okay? At a temperature of degrees Celsius, good. And a pressure of 0.889 atmospheres. Okay, lots of information given in that first sentence. Question, how many moles of oxygen did the student collect? Second question, how many grams of oxygen did the student collect? So, what is this question actually asking for? What variable? N. It's asking for N. Okay. So, if you notice that in a problem you are given one volume, one pressure, one temperature, and or one mole, and you're not given a second set of them, that means you're not using any of those laws you learned last week. You're not using Boyle's, Charles's, Avogadro's, you're not using any of those. You're using the ideal gas law because you just don't have enough information to use anything otherwise, right? Like you just don't. So we're gonna get to this last question, grams, at the very end. Let's get to moles first. So what's my gas law I'm using? PV equals nRT. Okay, so I'd like for you to write down your givens, set up your problem. What are we isolating here? What variable? N. So divide by RT on both sides. So my new kind of rearranged equation is moles of oxygen, so I just like to label what I'm talking about. Moles of oxygen is equal to PV over RT. Okay, now you absolutely cannot mess up unless you forget to alter your units. P, is it in a good unit? Yes, it's in atmosphere, so 8.889 atmospheres. V, is it in a good unit?
Yeah.
No, not for the ideal gas law. No. So if you go back, 1, 2, 3, spaces, 0.425 liters is what you are supposed to be writing in your ideal gas law. 0.425 liters. All right, all of that over, what's the big honking R value? 821 atmosphere liters per mole. K. Write out your big honking unit there. It's awesome. T. Converted to Kelvin. Good. 24 plus 273. 297 Kelvin. 297. 297 Kelvin. Okay. Once you set up, cancel your units, people. It'll be in your best interest because it'll make sure that you're in the good spot here. So you'll see atmospheres on top and atmospheres on bottom. They cancel. Liters on top, liters on bottom. They cancel. Now this one's funky, but deal with it. We have Kelvin in the numerator of the denominator. Yeah, because you see this is like the numerator of the denominator. And we have Kelvin in the denominator of the denominator. So top and bottom. Again, Kelvin, Kelvin, cancel. Moles is what I want. Isn't that the unit I'm looking for? Moles, so kind of double. It's like a double verification that you're in a good spot on your problem. Okay, so the moles of oxygen are equal to the numerator product divided by the denominator product, which is, I got this much for you. I'll find it. There it is. 0.0155 moles of oxygen. Woo, one down. Okay, so now we got A and we got our moles of oxygen. Our second question was what? Okay, how in the world am I going to get there? What's the molar mass? No. 32. I swear, I saw way too much of that on the test. If you put 16 again for O2, you don't even want to know what I'll do. You don't even want to know. Like, I can't even say it out loud. Okay, it's 32 grams for oxygen. So take your moles times your molar mass, and you get this magical number of 0.495 grams of oxygen. So ideal gas law is fun, right? It's just solving for x. It's algebra 1. Learned that in 8th grade, 9th grade. Yeah. Huh? This would be really easy for you then. It's very fresh. No, I'm just joking. Okay, 18. Thumbs up, ready? Okay, so I'm going to show you a variation of this in a different problem, okay? So, oopsies, 18. 18. What's the question? Okay, I'm going to go a little faster this time. An engineer pumps. What are they pumping?
5 moles.
Thank you. N is 5 moles of carbon monoxide gas into a cylinder that has a capacity of, what is that variable? V is 20 liters. Good. What is the pressure of the cylinder? So question is pressure. And it specifies it wants the pressure in kilopascal. We'll get to that as we need to. At 25 degrees C. So T is 25 degrees C. 25.0. All right. So what variable do we not have? We're looking for P, right? What gas law you guys want to use?
Ideal.
Ideal. There's really no other choice. P, V equals nRT. Solving for P. Divide by what? V. Okay. So P is equal to nRT over V. Tell me what I'm putting in here. 5.00 moles. Huh? There are 2 zeros, right? Yeah. Okay. 0.0821 atmosphere liters per mole K, which is the R value, times temperature. Darn it. I'm just going to move this stuff over here. So P is equal to nRT. What do I put for T?
295.
Lies. 298 Kelvin, right? So you're adding 273 to 25. All of that over 20 liters. So what unit does not cancel? What unit? Atmospheres, good. Moles on top, moles on bottom. Kelvin on top, Kelvin on bottom. Liters on top, liters on bottom. Atmospheres. So if you multiply your entire numerator and get your answer, then divide by your denominator, you will get 6.116 atmospheres. Now I'm taking out my decimals a little bit because this is not my final answer. Some of you guys made that mistake on your test quest thing. You only recorded like 1 or 2 decimals and it wasn't your final, so it actually caused some issues. So don't do that to yourself. You're working hard. Just keep a couple decimals extra and then make it your final call at the very end. All right, so our question was to get you up. Kilopascal. So what is that conversion from atmospheres to kilopascals? 101.3 kilopascals for 1 atmosphere. Atmospheres and atmospheres cancel. 620 kilopascals. You guys start number 19 without me. Don't be scared. Start with what you know. All right, who has any idea on how we're going to solve for molar mass? Go for it, Benny.
The STP, right?
It's not at STP though. See?
No. Oh.
We're given temperature different than STP and pressure different than STP. What's molar mass? What are the units? It's grams per mole, right? So molar mass is grams per mole. Do we know one of these?
Yeah.
Yeah, we know grams of this. So that grammage part's going to be used at the very end, okay? So we know the numerator. So what truly are we looking for? Moles, right? We're looking for N. Can you solve for N? Yes. Yes, you can. Okay, so let's do that first. P equals nRT, divide by RT, divide by RT. N is equal to PV over RT. P. What's P? Okay, now I do not care, like, if you show your conversion for that at all. You can just put in your calculator, 697.68 divided by 760 to get to atmospheres. You do not have to show that conversion. That's just an easy way to do that in your calculator. So this is 0.918 atmospheres once it's converted. V. 0.100 liters. Because you're taking your decimal back 1, 2, 3 spaces, so 0.1 over. You got this? 1000 liters, excuse me, thank you. Okay, so this R value 0.0821 atmosphere liters per mole K. All right, and T? Yes, so you're taking your 10 degrees Celsius, adding 273 to that to get that to Kelvin. All right, so hunky-dory from here. We cancel out everything but moles. Atmosphere's top, atmosphere's bottom. Good. Liters top, liters bottom. Good. Kelvin on the top of the bottom. Kelvin on the bottom of the bottom. Bottom. Cancels. Moles are left. The moles actually move up once you do your multiply by the reciprocal. So N of gas. What gas? Does it matter? No, not really. Fluffy dot chalk. That is 19.003953. Again, I'm extending decimals because I don't want any rounding error whatsoever. All right, that's not my final answer. So what do I need to do to get to molar mass? Mass.
And you divided.
Thank you. That's it. Grams divided by moles. Grams over moles. Divide. So take your 6.2. Your mass was 2.62, sorry. Grams over the moles you just calculated, 0.003953 moles. Basically what you're saying is this many grams is equivalent to this many moles, so of this substance. So this substance weighs, that divided by that, 662.8 grams per mole. Sig figs, what are round to? 663 grams per mole. Good. This is probably like some gigantic protein in your body, or no, that's a gas. Some sort of organic gas. Organic compound that's extremely volatile. Because you'll notice that eventually we're going to get to reaction stoichiometry, and I'll give you solids, and I'll give you liquids. Do you think you should put a solid or liquid in a gas law? No, it's called a gas law, right? You can only put gases in there. Whatever you get, like moles, it's going to be talking about the gas of the problem. So be careful about your identities, okay? Take a 2-minute stretch break. Go say hey to a friend, Mythbusters partner. Oh, Mythbusters, I'm almost done making comments, guys. It takes me about 10 minutes of experimental design, so that's 5 hours for all of y'all. It's going to be 5 hours to grade your test, so I just didn't have the energy after that. So work on that afterwards. Alright, I gotta finish checking homework here. One, two, three.
I only did one.
It's a lot of work.
Alright, I want you back in 30 seconds. Easy. $50. Don't they die after? Well, when is it supposed to turn? When is it supposed to turn?
It already smells like it.
I didn't even go back this morning. I meant to and I forgot. I will. Colin, did you have pumps at 13?
Like, here's what I like. I live in the place where my buses was shot.
Well, don't you have any like memorabilia or something?
Sorry?
Don't you have memorabilia or something from it?
Why did you forget?
Memorabilia. Do you have like something like keepsakes? Did you ever see that? Oh, Nick, I didn't see. Did I see yours? I'll check it out. Okay, and you're mine in 5, 4, 3, 2, 1, ready. Okay, so you know, for the chit chat, if you ask me a question later, I'm just not going to answer. Come on, people. All right, so we know LR. We love LR. We are so good at LR, right? Right, limiting rate. We are just awesome at this, right? So you need to have some knowledge of LR, and what the have is and what the need is and stuff before you can understand what I'm going to do right now, okay? So I'm going to show you a trick of LR. Because if I ask for you to do a problem, and the problem is more of a gas cell problem than stoichiometry, and you can easily interpret the LR, that's okay with me. But you have to have some background before you can understand this method I'm going to show you. I'm not writing anything down, okay? So I'm going to orally go over this. If you want to go from volume to volume, let's say I have volume of a reactant to a volume of a product. you know you have to have a balanced chemical equation, right? That's the only way you can get from something on one side of the equation to something on the other side, right? Well, normally what we'd have to do is we have to go mole-mole ratio, right? Do you remember me telling you that everything is related to the moles? So this is like you could go molecule-molecule ratio or liter-liter ratio. I'm going to use liter-liter ratio because I'm going from volume to volume. So the ratio between reactants to products is, for every 2 liters of hydrogen gas, I can make 2 liters of water vapor. Or for every 1 liter of oxygen gas, I can make 2 liters of water vapor. It's a liter-to-liter ratio, okay? So here's how you can do a problem like this in your head halfway, including LR, okay? So the problem said if 5 liters of hydrogen gas react with 4 liters of oxygen gas. Basically what I do is I write my BCE. Underneath it, I'm going to put 5 liters and 4 liters. Okay, but the rest is in my head. Basically what happens with LR is one of them runs out first, according to their recipe. Well, their recipe is right here. 5 liters of hydrogen gas, 4 liters of oxygen gas. For every 5 liters, I only require like half of that to react here, okay? So here's the trick. You take your your half of your one reactant divided by its own coefficient. So it's 5 divided by 2. 2.5. Take its half divided by its own coefficient. 4 divided by 1 is 4. That was a 2.5. That was a 4. The one that is lesser runs out first. Who runs out first? Hydrogen. This is your LR. Screw this. Don't even look at that the rest of the time. That's your LR. Okay? So you take your 5 liters. What's the liter-liter ratio from? Because the question says how many liters of water vapor? How many liters of water vapor can you make? How many liters of water vapor can you make from 5 liters? 5 liters. Because it's a 1-to-1 ratio, right? 2 to 2 is a 1-to-1. So basically what I just did in my head was figured out LR by doing this trick. And AP, I let them use this because stoichiometry is just a butt sometimes. You just got to get over it. You just have to limit it where you can. But if you know that's your LR, you're starting off with your 5 liters of hydrogen gas. And in your head, you were like, oh, I can make a 2 liter of water ratio to 2 liters of hydrogen. I know it's not natural because you're so used to mole-mole ratios, but this is liter-liter ratio. So 5 times 2 over 2 is 5. I can make 5 liters of hydrogen gas. Okay, so that's our stoichiometry relating to liters and not moles. It's just this is a good tool to use if you have constant temperature and pressure. Okay, thumbs up when you understand that. You got this. Okay, this is stoichiometry. Okay, we have reactions. So that's why I gave you that extra credit option for your test, because if you need to work on stoichiometry, do so in order to practice for this stuff and get credit back on your test. So it's a double-sided sword, because you have to know stoichiometry very well in order to succeed the rest of the year. Question?
I don't want to do extra credit, so.
Yeah, wait on that. Okay. So this is me walking you through how to do problems, okay? Write down what you want to. Basically, I'm going to start pulling together reactions in stoichiometry and the ideal gas law, right? Now, the ideal gas law, you can't just put any old thing in there. What do you have to put in there? Solids, liquids, or gases? Gases, right? So let's say I start you off with a reactant. Let's say potassium chlorate decomposes. What does potassium chlorate decomposing make?
Chloride.
And oxygen gas, right? You know you have to make it a gas, right? So making a metal chloride and oxygen gas. So I'm going to start you off with a solid reactant. I don't care about solids. I can't really do a whole lot with them. I also can't do much with grams. So what would I ask you to do first is probably go from grams to moles of that same solid. How would you do that? Molar mass. Okay. So then what you're trying to eventually get to, the question asks you to get to volume of a gas, okay? So your job is eventually get to volume of that product gas you make. Well, how have you ever gotten from a reactant to a product? Mole ratio. Right. You would just use your mole ratio from your balanced chemical equation. So this is normal. We take our grams to moles and then moles to moles. That's all normal. But this is moles of a gas now. Moles of gas. What variable is that? N. This is N. Okay. Because in the problem, I would also give you, I would give you a temperature. I would give you a pressure. I wouldn't give you a volume. I would not. So what your problem is, when you're reading the problem, you're like, oh no, I can't get volume of a gas because I don't have V or nor do I have N. But you have the ability to get to N. You can take your grams of solid to moles of solid, moles of solid to moles of gas. You got N now. So basically you got P, T, N, and if the question asks for you to solve for V, you plug it into your ideal gas law to solve for V. So do you see where I'm pulling these two things together now? reaction stoichiometry and gas laws? Okay, so this is if I start you off with some sort of solid, usually a reactant. Now, this is under non-STP conditions. But if I tell you it's STP, we're all good. You know your conversion for STP is 22.4 liters per mole. So you can only use that when it's at STP, but it says it's at STP, okay? So if I say, like, if I give you moles or mass of a gas, you can easily get to volume of a gas with that conversion. The last one is essentially the same thing. I'll show you in a second. But me doing a problem, I think it actually makes a heck of a lot more sense than this. This is just a kind of a general outline on how to solve problems such as this, okay? So the last one is, let's say I gave you, if I gave you a gas information, like maybe I give you the gas and it's a product. If I want you to go back to your reactant, like moles or mass of a reactant, that's a solid. You would just do that first step, but backwards. You would take your volume of the gas or moles of the gas, you go back through your mole ratio, back to your reactant, and then back to mass of the reactant, aka a solid here. So this last one, it makes less sense here, but it'll make more sense if I do it on a question. Okay, so let's do this. This is my example question I'm going to do for you, okay? Write her down. Write down the steps, okay? So, when potassium chloride decomposes, I'm going to stop here. What does it make? Okay, balance it.
3O2, 2HCO3.
Got you. Okay, so step one, know nomenclature, know how decompositions occur because they're different, and balance. Done. All right, step two, let's finish reading. Ready? All right, so when potassium chloride decomposes at 755 milliliters of mercury, what variable is that? Pressure, and 23 degrees Celsius, which is temperature, 4.26 milliliters of the gas. What gas is it talking about? O2 gas. Good. I'm going to label that. I want you to know that volume is regarding the gas. 2.46 milliliters of the oxygen gas is collected. Question. How much potassium chlorate, when I say much, what am I asking for? Mass. Okay, so I'm going to put grams right here. How much must have decomposed if none of the gas was lost? Okay, so all the information that I have, is it pertaining to potassium chlorate or the oxygen? It's the oxygen, right? Because we have a lot of information. We have the pressure at which the gas is at, temperature at which the gas is at, and the volume of the gas. What do we not have for the oxygen? Moles. Can I get to moles of oxygen? Yeah, using what? Ideal gas law, because this is all information that can go into the ideal gas law. Now, when I have moles of gas, how am I going to get back to mass of potassium chlorate? There you go. So you're going to eventually have moles of this gas from N. You're going to bounce back through mole ratio to get to moles of that, and then do what? Molar mass to get to grams. So basically, find out what you can do first, and then see if you can get where you want to go with it. It's problem solving at its best, right? So let's use this information to solve for N of oxygen, moles of oxygen, and then proceed from there. So PV equals nRT, solving for N, so what do? Divide by RT, divide by RT. I hope that you're writing this problem down, or at least watching. Mondays are awful. Okay, what do?
755 times 760.
Divided by 760? Right, that's like 0.998, I believe. I were missing those answer keys. 0.993. So that is work you can throw in your calculator, get your atmospheres, and no problem with that, okay? V? Good, 0.0426, because I have to convert that to liters. Over R, which is 0.0821 atmosphere liters per mole K. And temperature? Good, so you added 273 to that, 296 Kelvin. What units cancel? Atmospheres, liters, what else? Kelvin. So I'm stuck with moles. Yay, I wanted to be stuck with moles. So this is moles of gas.
How can this remote get
Because it's on the denominator of the denominator. And so it's the floppy dot shot thing where you put the, it's like multiplying by the reciprocal of this. You know this. Shut up. Okay, so this is NO2 of oxygen, which is, I got you here, 0.001741 moles of oxygen. Again, did I round? No, because I am not at the final answer yet. This is not my final answer. It's just a stepping stone. So now, what do? Mole ratio. So I'm just going to rewrite this over here. 0.001741 moles of oxygen gas. I don't care about oxygen gas. My question is regarding potassium chlorate. So what's the mole ratio? You got the BC in your paper, right? So 2 moles potassium chlorate. I hear you. Keep going. 3 moles of O2. Good. All right, did the question ask for moles of potassium chlorate? No. I'm actually going to keep going. I'm not going to stop here. Because I can see my moles of oxygen cancel, moles of oxygen cancel. I need to now cancel moles of potassium chlorate. So what do I have to do? Mass, 122.55 grams of potassium chlorate. That's just that added up. Over 1 mole potassium chlorate. And we're done, people. It's just a cumulative problem. 0.142 grams of potassium chlorate. Who feels accomplished right now? Woo! Like you know your nomenclature, you know your reaction prediction, you know your reaction stoichiometry, you know ideal gas law, you know units, you know pressure conversions, you know temperature conversions. Like you are super smart, okay? So use that and practice 1 through 5 on your paper. So we have about 25 minutes left. Yes, my first period is a little bit less enthusiastic than you guys are. You guys got stuff done. So 1 through 5 is it's underneath the 1 through 16. It says ideal gas stoichiometry lecture problems. Those 5 questions are due tomorrow. So what I did was problem set 14 is due on Wednesday. You can start. I crossed because I want you to focus on this. So you have to get through 1 through 5 done. You can start problem set 14. Okay, I'm not going to look for it. You can start tomorrow. So I want those 5 things done. Okay. So practice that for a little bit, and then I'll take questions on 1 through 16 that some of you guys have to do. Okay. All right. May the force be with you. I'll be around. 25 minutes. You should be able to get 4 done. Get all 5 done.